Dearly beloved, we are gathered here today to witness the birth of the Tobit Model. I'm going to go through now what the model looks like, the data it applies to, and derive the likelihood, and talk a little bit about the features of interest. This is going to hopefully help you in making the pace at the lectures seem a little easier to follow, and also hopefully help you when you're reading up for this topic. Alright, so let's start with talking about the empirical setting. This is the type of data that the Tobit model was born to work with. As you can see, we have a mass point here at 0 and then continuous values of our y variable. And if we plot y against x, this is the typical picture that we have in mind. That as x increases, we see that y starts to increase, but there are a bunch of values here down at a 0 that are what we call censored or truncated. And this can arise due to either corner solutions or censoring. Two very important distinctions that we will talk about in the lectures. What we're going to do with the Tobit model is basically to formulate a model where we think of a latent index that we do not observe, but which is there somehow, looks like this, and then that's what we're going to model, and we're going to think of the regression line going through the red cloud as a kind of a standard linear model, and then this truncation at 0 is something that happens. So we may be interested in the true red lines down here if the blue dots are censored. For example, if due to anonymity we cannot see them. But if there are corner solutions where you just cannot choose to work negative number of hours a week, we're actually interested in the blue dots. But the red dot is a tool for us to understand what happens. Okay, let's look at what the model looks like in math. This is the latent index, the red dots, if you will. It's the standard x beta and a standard normal error term, or rather a normal error term with variance sigma squared. And then what we observe, the y we observe, is the maximum of this latent index y star and 0. So in other words, if y star is negative, we only observe a 0. So that's what happens here. Here y star is negative, so we only observe a 0 here. And this gives rise to the mass point of y's observed at 0. Here we have it as well. We can code this up in MATLAB like this. A function that takes a number of data points you want and a parameter vector. Then it packs out the beta and the sigma from theta. And it draws some x's. You can see there's a constant here that's n, a row vector of n ones, and then a vector of random normals. So it doesn't really matter what the distribution of the x's is. In the model, that's not really specified, so that's up to us. It should work for any distribution of the x's, or most distributions of the x's. Of course, one thing that can't break down is the rank condition. Then we compute the latent index y star as x beta plus sigma times a new random normal, which is the noise term, that's the epsilon up here. And when we multiply that by sigma, it gets variance term sigma squared, or standard deviation sigma. And then we construct y as the maximum of y star and 0. So that's the sense in which the model is really a recipe for how we generate data. Okay, so how do we get to a criterion function so we can actually estimate this? Let's take a step back actually and look at a linear model first before we go to the Tobit model. So in the linear model that is OLS, but with let's derive the likelihood function for OLS just to remind us how we derive likelihood functions. And then afterwards, we're going to derive it for the specific case of the Tobit model. So the steps that we go through when we derive the likelihood function for just the linear model, OLS, is that first we find the CDF, uppercase F, we typically denote it. That's defined as the probability that the stochastic variable y is smaller than or equal to yi. That's how we define CDFs. And in other words, if we insert the definition of the stochastic variable y, here yi is thought of as a realization, and this is the stochastic variable, so we insert the stochastic variable here. The probability that that's smaller than the realization yi is written here, so we've inserted the definition. Now we isolate epsilon I. Why do we isolate that? Because that's the only thing up here. X beta is, we're conditioning on x, so x is just given and beta is just a number. So epsilon is the only thing that's random. So we isolate that here because this is how we write CDFs. The probability that the stochastic variable epsilon is smaller than some number. Problem is that epsilon we don't have the CDF for. What we have is that epsilon is normal but has this sigma term. But fortunately this is an inequality, so we can divide on both sides with a positive number sigma. And now what we have is epsilon over sigma. That's standard normally distributed variable, smaller than or equal to some number, yi, the realization yi, and xi beta, which we're conditioning on. The probability that a standard normal is smaller than some number, that's capital phi. That's what this function means. So now we've derived the CDF. Step 2 is then to find the PDF as the derivative of the CDF. So we take the derivative of this guy with respect to what? With respect to this number, yi, little yi. And when we do that, we can see that little yi is multiplied by 1 over sigma, so that comes outside of the CDF like this. Then we take the derivative of the CDF. The derivative of uppercase phi is lowercase phi, and we've already multiplied with the inner. So that's how we get to the PDF. Okay, so step 1, find uppercase f, and then we find lowercase f. Now we're ready to attack the Tobit model. Except that we have one challenge. We have made assumptions on y star, but not y. So y has this maximum, and we'd really like to work with y star. The solution is to work with the elephant strategy, as I like to call it. How do you eat an elephant? Piece by piece. So we split the function up into 3 different functions. One if y is negative, one if y is 0, and one if y is positive. The idea with doing this is that in each of these we're going to be able to get down to something with y star. And note that we can always split functions up like this. That's always allowed. And why does the split make sense? Well, because the probability that we observe a y that's negative, well, that never occurs. So the density over here is 0 everywhere. Here at 0 we have a mass point. And then greater than 0, it's a continuous density. Alright, let's do this with some math here. Okay, case 1, if y is negative, this never happens, as I said, so the density is just 0 for all y less than 0. In the second case, when is y equal to 0? When do we observe a 0? That happens whenever the latent index is 0 or less than 0. Okay, so the density at 0 is the probability that y star is smaller than or equal to 0. And we're gonna look at this later. What about when y is greater than 0? Well, that happens whenever y star is greater than 0. And that's nice because then y star is equal to y. And so they have the same PDF on these points. And this is nice because this is just the OLS density. That's just what I derived on the previous slides. So that's really nice. So the only thing we're missing is this guy here. Okay, case 2. So this is what the model looks like. Y star is x beta plus epsilon. And at the lectures, we're going to show that the probability that y star is smaller than or equal to 0 is 1 minus uppercase phi of xi beta divided by sigma. You can already get the sense that the way we're going to show that is by inserting the definition of y star here. That is, inserting this guy, and then we isolate the only guy here that's stochastic, which is epsilon. And then we have to get to something that we can evaluate, so we have to make sure that whatever is on the left-hand side is a standard normally distributed variable so that we can use the normal CDF. And finally, we're going to use symmetry, but we're going to look at it in the lectures. In the case when y is positive, well, we're going to show that it amounts to the PDF from just before, but basically the derivations are exactly as I showed you just before. So when we put it together, this is the solution for the density. It's 0 if y is negative, this number here if y is equal to 0, and then it's this number here, the OLS density, when y is positive. So the Tobit log likelihood looks like this. If y is equal to 0, it's the log of the first guy, and if y is positive, it's the log of the second guy. So we can code that up in MATLAB in the following way. Suppose we have some criterion function here that takes y and x and theta. Then we pack out the parameters. So sigma is the last parameters in theta, and beta, that's all the other parameters, so from 1 to the last one minus 1. And then you can see how this indicator of y equal to 0 is written in this way in MATLAB. And it's an n by 1 vector of indicators, so we use dot times to ensure that it's element-wise multiplication with this term, which is just the MATLAB equivalent of this guy. And similarly, we can use this y greater than 0 dot times the other expression to get at this part of the likelihood function. And then, since we're going to do M estimation, we're going to return the negative log likelihood. Alright, so there are a number of features that we may be interested in when we're working with the Tobit model. And these features are that's the stuff that makes sense, the predictions that we have for y and the derivatives of those. So if we want to be able to ask actual questions, these are the ones that we'll use to answer them. One of the interesting features is the conditional expectation of y conditional on x and on y being positive. In other words, if y is wages and x is years of schooling, then this is the expected wage conditional on the years of schooling you have and on you actually participating in the labor force and not having zero wage. Alright, so this is how the algebra works for deriving this conditional expectation. Take the expectation of y conditional on x and y being positive, and then we note that whenever y is positive, y is equal to y star. Because yi is the maximum of 0 and y star. So when yi is positive, they're the same. So we insert y stars. Then we insert the definition of y. You can see that I have a u here instead of epsilon. But that it's just the error term. So x beta plus an error term, and then conditional on x beta plus the error term being positive. Take this x beta outside of the expectation, and we can do that because we're conditioning on x. Beta is just a number, and when we condition on x, x is also just a number, so they pass out of the expectation. Okay, so now we have the expectation of u conditional on x and x beta plus u being positive. What we can do here is we can first isolate u on here. We do that by subtracting x beta on both sides of the equation. So we have minus x beta, and then we divide by sigma. We can do that on both sides of this inequality because sigma is positive. So now it reads u over sigma greater than x beta over sigma and a minus in front. Okay, we also have a sigma appearing here. So sigma is just a number, so we can multiply and divide by the same number, and then we just take one of them outside of the expectation. Okay, why did we do all of this? Well, again, we know that u divided by sigma is standard normally distributed. So here we have the expectation of a standard normally distributed random variable conditional on that same standard normally distributed variable being greater than some number. This expression, the expectation of a standard random normal conditional on that standard random normal being greater than some number, turns out you can write it like this. The derivations are in the slides. And then we can use that this guy, the top guy here, little phi is symmetric, so phi of z, phi of some number is equal to phi of minus that number, so this minus goes away, and 1 minus uppercase phi of a negative is equal to uppercase phi of the positive of that number. So we can use symmetry to simplify this thing a little bit. But we just generally write this fraction here as lambda, and the fraction is equal to this thing here as well. So this is called the inverse Mills ratio. It's an important thing here because, as you can see, the expectation of y, which what we're interested in, the expected wages conditional on participating in the labor force, depends in this fashion on x beta, but there's this other part here that also depends on x beta. So we can, this Mills ratio, you can interpret it as kind of an omitted variable bias. So if you were to just regress y on x with OLS, you'd get biased estimates of beta because you would be omitting this term here. So the truncated density in the inverse Mills ratio, this part here, this step, comes from the fact that, or rather to derive that, you have to think of it as a truncated density. So the density of a random variable conditional on that random variable being greater than some number. If we take the expectation like this for a conditional on a being greater than k, then we can show that that's equal to this thing down here. That's exactly what happened on in the derivations before. That's what happened in this step, is that the expectation of a random standard normal variable conditional on that standard normal variable being greater than k is equal to phi of k over 1 minus uppercase phi of k. The derivations here are going to be in the slides that you get for the lecture, and you can look at them at your own leisure. For so the other feature we can be interested in is the unconditional expectation, e of y given x, not conditioning also on y being positive. Turns out that's equal to this expression here. So it's x beta scaled by this thing plus this other term here. So it's not as easily interpretable as the other guy, except that as x beta grows towards infinity, this thing becomes 1, and this converges to just x beta times 1, and as x beta goes to infinity, this thing here goes to 0. So the whole thing goes to x beta as x beta increases. And to show this, we're going to split this thing up in saying that there's some probability of one event occurring times the expectation if that event occurs, plus a probability of another event occurring times the expectation conditional on that event. And this guy here we already solved for. And this thing here will turn out to be equal to 0. And these things can be coded up in MATLAB, and as you can see here, the first term here, e of y given x, is x beta dot times normal CDF of x beta over sigma, and as I'm sure you can see, this is really similar to the equations, or as I hope you can see. And here we use the function for the Mills ratio that we define over here to get at this guy. And here are the two features. So you can see that the expectation of y given x comes down to 0. That's the expectation where we don't condition on positivity. And you can see they become linear here towards the end. And the conditional expectation where we also condition on y being positive, as you can see, that one's always bigger than the red line, but they converge to the same thing, namely just the linear function in the end. And that's all for this online section.